We have okay, I think I figured out how to record this so that I can upload it when we're done. Okay. Those of you who have been in my office hours before know that I've been working on a study guide for the final. No need. This is what I have so far. It's just the 12 reactions you need to know, the 10 you've covered so far in class. And it basically breaks down, it's like a simple example of each reaction, right? So we have acid-base chemistry, addition to alkenes, and then I've been throwing in some definitions that you should know, like what is an alkene, electrophilic, nucleophilic. Each mechanism step is written in red, and then I have the explanation in blue. Hello? Okay, maybe this is not as seamless as I thought it was going to be. I do it like this. Wait. JK. Okay. It's just slow. Okay. For each mechanistic step, I have an explanation of what's going on with the arrows. And for complicated reactions where there's a whole bunch of steps, they're numbered. Because I know when I was taking orgo, something I struggled with was, where do these arrows start? There's like 5 of them. I don't know what the starting point is and what the ending point is. So for all of these, I've numbered them, like especially when we get to reductions and oxidations, there's 6 arrows in one step here. So this gives you the flow of what to follow. Helpful, not helpful, somewhere in the middle. Okay. So far, I just have the reactions. I'm also going to do like concepts. So like aromaticity, chirality, resonance, functional groups. But I haven't done it yet. I've just done this. Would you like me to upload this now or wait till I have a completed document? Okay. I'll upload both. But I'll put this up for the people who want it now. So, office hours. Who has questions? Oh my God. Oh, I left my pencil upstairs. I'll be right back. I need my keys. While I'm gone, think about what you want to go over. Me too. Me too.
Well, my roommate, she's taking like CHEM2 right now, and then I told her like what's on her test and like functional groups and like she's like, how do you have that on the same test? Like, we're just now learning this thing. Because of us. He does it because like I have to take a video and I'm asking questions on the and then he gets like you were just
What do you guys have questions on? What do you have questions on? What? 320? How about some more specific questions? Okay. So let's start with problem set 7. Who has questions about what was covered today? Yeah. Okay. Let's look at that. Okay. So question 2 was the question where it asked you to identify the steps. Let me know if this is not big enough for you guys. So this first question, or the first part of this question, was on prelim 2. This like exact example from prelim 2. So this is electrophilic aromatic substitution. What's an electrophile? Electron deficient, yeah. And is a benzene ring aromatic? Yes. So we have the two things we need for electrophilic aromatic substitution, right? We have an electrophile, a cation or a positive charge is going to be electron deficient. So we have our electrophile, our benzene is aromatic. So when we add to that benzene ring, the faster step is going to be losing the proton to restore aromaticity. So that's how we get our first step. The next step of the reaction. So an aldol addition is when you're going to take two acyl groups and you're going to make the ald or an aldehyde or a ketone of some kind and an alcohol. So with this one, we have our ketone here and our alcohol here. And in our starting material, we have this acyl and this acyl. So when looking to recognize reaction types, having those two acyls is indicative of one of three reactions. You could have Claisen, you could have aldol, you could have acyl substitution. Looking at our end product, we can narrow those down. So because we have everything added together, it's indicative of an addition. So that's where we get that this is an aldol addition. Questions so far? Yeah.
You said we need two acyl groups.
So first look at it, we see the two acyl groups. That narrows it down from our 10 reactions to 3 reactions. Claisen, aldol, acyl substitution. An acyl substitution would mean that we kicked off one of these groups, but we don't. We see everything attached at the end. Between aldol and Claisen reactions use ethers. So that's where it's like this, or actually JK, haha. So our claisen has to have those two oxygens that are like right next to each other, while the aldol is just that acyl group. Is that clearer? Okay, can I move to the last step? Okay. We're gonna go this way. So with this, we have one nucleophile replacing another nucleophile. So nucleophilic substitution. Because we substituted OH minus, which is a nucleophile, for Br minus, which we got from HBr. Yes, no, maybe so. Confidence levels. Yes.
Could you do a claisen reaction next to an aldol reaction?
Yeah.
And just like show us all the differences?
Mm-hmm. Before I move on from this, any other questions about this question? Yeah. So nucleophile just means electron rich. So basically anything that has a negative charge, you can consider a nucleophile. So, well, ones that are not negative. Some examples of nucleophiles. You have SH, NH2, OH when they're attached to other things, because all of these three can be deprotonated. And when they're deprotonated, you get S minus and H minus and O minus, which NH2 also has that lone pair. So it doesn't even need to be deprotonated sometimes. Some other nucleophiles. This group and almost anything that has a negative or a lone pair. Okay. I'm going to cheat a little bit here by just showing you the study guide, Hallie, to answer your question. So this is an aldol addition. You have two different ketones, right? So I'll do this in a new color. Okay. So we have one ketone here and one ketone here. One of these will be deprotonated. How do we know where it will be deprotonated? Starts with an R. Resonance. So these double bonds, an anion here can be stabilized by this pi system. because we can push those electrons here and have the oxygen hold the extras. So what on this molecule is the other fairly likely site of deprotonation? If we were to number our carbons 1, 2, 3, 4. What other carbon has access to that resonance form? Not quite 2. 1. So if we put a negative here, we could see that same movement. Okay. So we have 2 ketones here. A base is going to come and deprotonate at the selected site, and we will create an anion. So we get here. Between oxygen and carbon, what is more electronegative? Oxygen. So when we see a site like this, we have to remember our partial charges. So because the difference in electronegativity is so great, the oxygen will have this like half negative charge, and the carbon will have this half positive charge, meaning it's electrophilic. And this one is nucleophilic. So an anion, would you say that's electron rich or deficient? Rich. So we also have a nucleophile here. Our nucleophile is going to attack the electrophile, indicated by this red arrow, and then that pushes electrons up onto the oxygen. Because it's electronegative, it has the ability to hold on to more lone pairs and still be stable. So now that we've created that bond, we have this structure. This structure is called a tetrahedral intermediate. And that's because this site is tetrahedral. It's now a carbon with 4 non-hydrogen things coming off of it. Tetrahedral intermediates, not stable. So they fall apart really easily. That's where you would see a condensation. But because we have this base that we protonated earlier, it's now ready to give back that hydrogen. So we're going to protonate using an acid, and we end up with ald, like a ketone aldehyde, all, like an alcohol. So an aldol addition will always end with one of these double bonded oxygens and one alcohol. If you don't see that alcohol group, that is a condensation. And that's where we see the loss of the hydroxy group. Condensation, like water forming on the outside of a cold beverage, we see water formation. Claisen reactions. I have it kind of spelled out here. Claisens are going to use ethers. Aldol reactions are going to use ketones. So the key difference here is this oxygen. Oh, hey, wake up. Okay. This oxygen, in our aldol reactions, there's not a secondary oxygen in these molecules. So our Claisen reaction is going to follow a very similar mechanism. but we're gonna lose one of those secondary oxygens. So we have the same first steps where it's base deprotection or deprotonation, and you make the anion, that negative charge. It's then gonna attack the carbonyl center here and push those electrons up onto the oxygen, just like the aldol. Here is where it gets different. This tetrahedral intermediate is going to break apart. So the oxygen is going to push its electrons back into the system and kick off that secondary oxygen group. That secondary oxygen group is going to have a resulting anion that's going to be protonated. And our final product is two different molecules. So in an aldol addition, you're taking two things and turning them into one. An aldol condensation means you took those two things, turned them into one, and water. Claisen, you took two things, you now have like 1.5 and a half. Yes.
Does that oxygen always come on?
Yes, that's the principle of the Claisen reaction.
And it's always the one that only has a single bond, never the double bond.
Yeah. Because this one doesn't have the one that's incorporated into the carbon chain doesn't have the spare electrons to push around to kick something else off. It's locked up in that conformation. Yeah, truly. Yes. Alkenes. Are they going to be electron rich or electron deficient? They have extra electrons in their pi bond. So rich or deficient? Rich. So our alkene is going to act as a nucleophile. Carbocation. Rich, deficient. Deficient. That's going to be our electrophile. So attack is always going to come from the nucleophile. Remember that when we're drawing our mechanism arrows, the starting point, we're always following electron movement. The starting point is going to be where those electrons come from and where they land. So this double bond is going to attack that positive site. That is ugly. So because we gave those electrons up to make this bond, we've now created this carbocation. There are two options here. We could have some nucleophile in the solution attack there, or this proton is going to be removed. if we were to have a nucleophile attack here, we would lose aromaticity. The resulting structure would be this, and it's not aromatic. So instead, we're gonna have some base come in and abstract the proton so that these electrons can be put back in the system. And thus, we have an aromatic system still. Julia, yes, no, maybe so. Okay. How do we feel about the concept of aromaticity? Good? Shaky? Remember that aromatic it has to follow this equation where 4n plus 2 equals the number of pi electrons you have. N has to be a whole number. If it's a half number, then the system is anti-aromatic. And if you don't have a conjugated system to begin with, the whole thing is non-aromatic. Thumbs up, middle, down.
Can you show us an example of calculating that?
Yes. You can kind of think about aromaticity like a flow chart. So, is it a conjugated system? Does everyone know what I mean when I say that, or should I put it in other terms? In other terms, it basically just means, can all the pi electrons talk to each other? Are they all connected in some way? Okay. So if the system is not all connected, you can stop there. It's not going to be aromatic. If they are all connected, then it moves us to our next question. How does it satisfy the 4n plus 2 rule? If when solving 4n plus 2, you get a whole number then it's aromatic. If it's a half number, it's anti-aromatic. So let's work through this example. In this system, are all the pi electrons conjugated? Why? Resonance. So it means that we can move this around and move this around and move this around and move this around. And move this around. And they all can talk to each other. So we have a yes here. Now we can count our electrons. 2, 4, 6, 8, 10. Pi electrons come from double bonds or lone pairs. So we can plug it into our equation. We can do a little bit of algebra. Whole number or half number? Whole number. So this is aromatic. Up, middle, down. The few of you that participated give me ups. So I'll move on to the next question. Yeah.
Could you do an anti-aromatic?
Yeah. Do you know when you guys covered aromaticity? Around what lecture? Anyone? No? No takers? Uh-huh. Okay. So I got it. Okay. One of these is aromatic, one is anti-aromatic, and one is non-aromatic. Which is which? I'll give you guys like 2 minutes to think about it, and then have someone come up here and tell me what they think. Anyone think they have an answer? And feel confident enough to share? Tell me the first one.
Actually, the first one, last two.
Okay.
The second one, I think is anti-erratic. The third one is
So if I told you there's one of each up there, and you just identified two, why don't you do me a favor and identify the third?
yes, that one. Non-aromatic.
Come on. You're right. Yeah.
Is that because, so in the first one, the one I can do, resin structures, and two, I have the 6 different, things, the 2 pylons and the addition of pairs. But then in the second, I still can do the resonance structures, but it's not for this two.
Yes.
Okay.
So
You can do the resonance structure.
So you can't do the resonance structure because remember that we have implicit hydrogens here. So if you try to move either of these double bonds from here to here, there's nowhere for those electrons to go without kicking off the hydrogen or opening up the ring. And that's not a resonance form. A resonance form means that you cannot be breaking any sigma bonds, which are like the initial connection between your carbon points. So this one doesn't have a conjugated system because there's nowhere for those electrons to go. They don't have any delocalization. So you could try and push it this way, and then this one would be overloaded, so we'd have to push this way, but then you run into this problem again. So there's no resonance here. But this one, the second one, you can push this here and make this. And then you could continue pushing around, putting the carbocation basically on every position. So you do have the conjugated system. So now we do our equation. We have 2 from this pi bond, 2 from this pi bond. N equals 1/2. So it's anti. This one, if we do our counting again, we get 6. We get a whole number. So that means that this structure is eligible for electrophilic aromatic substitution. Because it's aromatic, all it would need is an electrophile. One of the main things that was missed on prelim 2 was that question about electrophilic aromatic substitution. The problems that came up a lot were not counting your carbons. So you have 6 carbons from the ring, and then you have 2 from your addition. So there were some answers that were drawn like this. You've lost a carbon because you still have 6 in the ring, but now you only have 1 additional one. Another common mistake with this question was not considering the multiple products that could be formed. In this example, from the homework question, all of the products will look the same. But on the exam, it looks like this. That oxygen can push electrons in, and eventually you'd get resonance forms with anions here and here. So there were two possible products from that reaction. Questions, comments, concerns? Yeah.
How do you know, like, I know we talked about this before, but, like, when it's okay, like, can you cover, like you, so it seems like, oh, you should be able to time this time, but sometimes we're not like.
Can you be more specific? Like with this question in particular?
Yeah.
So
I think that's why it was like, it was kind of confusing.
So with this one, it circles back to this stuff. We lose that proton because the more stable and faster reaction is going to be the loss of that proton versus the addition of something else. And that's because things that are aromatic have more resonance forms and are therefore more stable. So with aromatic stuff, you will always see the loss of that proton to restore aromaticity. Other questions?
So what was the
So on the homework, it was just a simple benzene ring. This here. There's no substituents on that ring that would direct a reaction anywhere. The resonance, the only form is going to be moving the bonds around. And that doesn't really change anything. With this one, you have a lone pair here that could push down and create this minus. And then if you wanted to go further, it would push this down and create this anion. And it can technically go one further, like this. But the red and the pink are going to be the same because they're symmetrical. So they'll look the same. This one?
Yes.
The problem with that one is you lost a whole carbon. So this 1, 2 here, you've lost the connecting carbon, this carbon here. So although you attacked that cation, you have to remember that this group is separate. And what you've just created is the bond between them, which would be this line. Yeah. What specifically? Just like all of fatty acid? Okay. Yes, I can do that. So the thing with fatty acid biosynthesis, you have all the reactions you need to know in your repertoire already. Where it gets complicated is seeing that application in real life. And I think the box can be confusing for some, and that's okay. We'll go over it. So basically, he gives you this box, right? Fatty acid biosynthesis is 4 reactions that we know. The first one is performed by the enzyme ketosynthase. But the reaction as we would recognize it, the Claisen. Step 2 comes from a keto reductase. Can any of you infer from the enzyme name what kind of reaction it might do? Reduction. Number 3 is a dehydratase. It's going to do an elimination. And our last step, enoyl reductase, which is probably going to do reduction. So the first steps of fatty acid biosynthesis, you guys will recognize as acyl substitution. For those of you who've been to my office hours before, the acyl substitution reaction, what 2 things do you need? Double bonded oxygen, because that's your acyl. And what else? Sort of. Whoever said base is the most right so far. A nucleophile. So you need something that you can deprotonate. So that could be OH, NH2, SH, any of those. So there's 2 parts that come together for the first step of fatty acid biosynthesis. We have this structure, which is called acetyl-CoA. We also have this structure, which is called malonyl-CoA. Your first round of biosynthesis will use one of these and one of these. Every round from then on, you are just adding acetyl-CoA. So fatty acid biosynthesis, you're increasing by 2 carbon every round you do. Those 2 carbon come from acetyl-CoA. The most complicated part of fatty acid biosynthesis is getting it all set up. So let's get into it. We have these 2 files, right? We're going to take them and copy paste. The first step is loading our acyl-CoA, acetyl-CoA. So we have this start. Also, if it's easier for you guys to think of CoA as just R, you can do that. CoA is not something you need to know. It's short for coenzyme A, which is a super long chain. That's why we shorten it to CoA. The most important thing to take away from S-CoA is that it's a thio connecting a carbon chain and a carbon chain. And that CoA can easily leave. So we have our S-CoA. Like I just said, easily leaves. The first thing that's going to happen here is we're going to deprotonate this thio. Oh, another thing to give you guys context. Who knows what ACP means? It means acyl carrier protein. It is going to carry your acyl group around to all the stops at the biosynthesis factory. It is like the long arm that can reach out into the solvent and grab the pieces you need. That is why everything will start on that acyl-CoA, or on that thio from the carrier protein. So now that we have primed our hook, basically, we're going to catch a fish. This negative electron rich nucleophilic, the carbonyl is going to be anyone? Electrophilic. So we'll have our nucleophile attack there. And it's going to form a tetrahedral intermediate that is then going to break and kick off our CoA. So we get this. We are then going to pass this on to our first step. So we're going to have another base come in, deprotonate that. I'm just going to erase it, put the negative. This is going to attack our carbonyl, make a tetrahedral intermediate, and then kick it off. So we're here. That other starter unit I talked about, malonyl CoA. It is now his time to shine. So to draw this out in full form, this is just, all I did here was change the COOH to its like fully drawn out form. So now our nucleophile can attack our electrophile. We'll form that tetrahedral intermediate and we'll kick off CoA. Everyone following so far? It's easier to take the questions as they come rather than going back through the whole system. So as you have questions, stop me and ask, Hallie. Yes, I will tell you when we're past the first. Technically, we're not even at the first step. We've just officially loaded our protein. No. Yes.
And so where is, like, are all of these just in the reaction together, like this, is just randomly there? Or like,
Yeah.
where is it?
So this actually happens in our body, and the acetyl-CoA and the malonyl-CoA are right there. They're not right there, like super close. That's why there's the acyl carrier protein, because it's kind of like the forager that goes and finds them and brings them to this reaction. Yeah. In biological systems, as well as for most of our purposes, you always want to remember that water is there. This is too skinny. As H plus and OH minus. And so that OH minus is ready to accept the protons from our system. It also means that those H pluses are there whenever we need them. So just kind of always assume that this reaction is in the background. Yeah. Yeah, so it's basically leaving as S for A minus. And the reason the red and the yellow are different colors is because they're technically different steps, because you have that tetrahedral intermediate formed and then you have it falling apart. But for the sake of space and time, I'm just condensing them into one step. Yeah. Yes. The arrows too, or just the like general steps? Okay. Then let me do a different naming system. So A, B, C, D letters are like big steps. Numbers are electron movements. So now that we have our protein loaded, we can actually do the chemistry now. Just getting started on that stuff. Can I zoom in to the edge here, or do people need this whole picture? My hope is that this is all recording really beautifully and I can upload it as a video. If not, I can also upload this whole like PDF that I've been writing on. Okay. So we're gonna have another base come in and take this proton. And it's gonna create carbon dioxide. And carbon dioxide will leave and we will generate an anion.
So are we starting step one?
Yes. Does everyone follow the decarboxylation?
Is the curly, or like the curly wavy line from S to ACP, is that the one?
It's a flexible linker. So it's basically just saying this is connected and it's wiggly. So what do you guys recognize here? We have a nucleophile and an electrophile. They're going to react. So our nucleophile will tack here. We'll form that tetrahedral intermediate, and then we'll kick off of step 1. Yeah, Julia. They become this anion. So they become a lone pair on this carbon. Are we ready to move on to step 2? This part? So this negative created a bond here. So we'll see when I draw the next step here that it's now attached here. Basically, this whole part is step 1. Everything before this was just loading the protein. So now we have and we lose the whole group. In practice, it looks a little bit more like an aldol than a claisen, just because with the claisen reactions we've covered, the H has always been like another carbon group. Mm-hmm. So we've moved to step 2. Our next little corner of the protein. Step 2 is a reduction. Can anyone tell me a reducing agent they know? NADH. So NADH is one of those structures that you're just kind of going to have to memorize. It's super useful for our class. Reductions and oxidations both use the same general principle when it comes to NADH. This is NADH. You have to draw the R on there because NADH is actually a huge molecule. This is just the active part. So we abbreviate the rest of it as R. So for a reduction, we're going to reduce one of our aldehydes, well, ketones, to an alcohol. To do that, we are going to do a hydride transfer. Does anyone know what the difference between a hydride and a proton is? So hydride equals H minus. Proton equals H plus. So a hydride transfer is when we're taking the proton and its electrons and moving it somewhere. So in a reduction, remember oil rig, oxidation is losing, reduction is gaining. We're going to reduce one of these aldehydes. So we're going to gain the electrons. So we're going to move a whole hydride instead of just a proton. How we do this is the lone pair on the nitrogen is going to push up into the system. This carbon is now overloaded. So we're going to push the double bond up. This carbon is now overloaded. So we're going to transfer the whole hydride. I didn't mean to. They're not connected. I'm running out of space. Didn't leave myself a lot of room to work with. So this carbon is now overloaded. So we're going to see electrons come up on the oxygen. So, yeah.
The exam in electricity, is it usually like that plus the other molecule? Is that how you
Yeah.
write it?
So in reducing our molecule of interest, we have oxidized NADH. So NADH is our reducing agent. It gets oxidized to NAD. Our starting molecule is called our oxidizing agent. It is reduced. And we have our next step here, which then will get protonated by something in the system. So it's drawn in the protonated form. And that's step 2 of fatty acid biosynthesis. To where?
Just so we can see like the step.
Oh, out.
Exam where this will be like, we have to identify or we have to draw this entire process, just draw the step of the process.
How many times I gotta tell you I don't write the exams? I don't know. When I know, I'll hold an office hours. step 3, anyone? Oh, yes.
So the OH that we got right here. Can you see?
No. So the O minus is the like actual product of the reaction. But like we said earlier, we can always remember that water is there in H plus and OH minus. That O minus would attack the H plus. We would get the protonated alcohol.
I have kind of the same question. That happen because oxygen is losing its double bond, and so it's going to, so it's order to keep stability, it's going to get the hydrogen.
Yes. Other questions about step 2? To step 3 we go. Who remembers what step 3 is? Elimination. Who remembers any mechanism of elimination? Slay. No one. Okay. So elimination is where we form a double bond. And in this case, we are going to do so at the expense of water. So another term for this is condensation, as we lose the water. So we're going to deprotonate. So we need X minus of some kind. This here proton. Let me double check. Tomorrow at 3?
Do you have any, what about?
Every
Are you gonna
week.
have, like, another one, like, at around this time? Or is it
Oh,
just for today?
this is like halfway between our prelim and our final. And there was a lot of time between the prelim 2 and the final, so I'm having this one. So the next one that's like evening unlimited time will be closer to your final. Yeah. It is implicit now. It has gone nowhere. What? Yes.
Why did you lose the H from outside of it?
Because we don't, so they're not the same hydrogen. This hydrogen came from NADH. This hydrogen we care about because it's about to do chemistry. Yes. You guys want to go over step 3 or chat or? Yeah. So step 3, we're going to deprotonate. X minus is going to take this proton and form an anion here. This anion is going to come up into our system and kick off water. Now you may be saying, Jess, it's not kicking off water, it's kicking off OH minus. Water is always in its ionized form, so you have H plus and OH minus. So you have H plus that will turn it into H2O.
Is that connected to each other or is that a whole different thing?
Here. And that is step 3.
Did you repeat what you said about the water?
So you may be thinking, Jess, this is going to be OH minus. OH minus and H2O are not the same thing. But that H plus, they're always in equilibrium to make water. Yeah. How do we feel through step 3? Only one step left.
When you drew the H2O, I'm assuming that's just.
Yeah. So, who remembers what step 4 is? Reduction. It's going to look a lot like our other reduction. We're going to use another molecule of NADH, and we're going to reduce this double bond. Actually, check it. Why does our hydride attack at the yellow position and not the green position? Yes. Yeah. So our final product, when we attack at the yellow, we create the anion at the green. This is stabilized with resonance talking to that double bonded oxygen. So that's why the anion will form at that position and not the other position. This anion is going to be neutralized by a proton that's in the solution. And we get this. So this can now continue to go around. Also, let me be consistent with my numbering. we're back around to the top. If we had another acetyl-CoA, we could do it all over again and keep building. Yes. So the only thing that's left is termination, and that means kicking it off the protein so it can go be free. And basically, what happens with that is you'll have water come in. So I'm gonna do okay. Decades of hard work. So yeah. You know that OH minus that's been floating around? She comes back. She's gonna attack here. We're gonna form the tetrahedral intermediate. We're gonna kick it off. Our final product will be right. 1, 2, 3, 4. 2, 4. Yeah. And that is fatty acid biosynthesis.
So where did that?
It's still there. This is just its own thing now. So easy, right, guys? I don't know. I just work here. So do we feel better about fatty acid biosynthesis? You guys have all the tools you need to do this chemistry. Like, you know the aldol reactions, you know reductions, you know eliminations. The difficult part is seeing those concepts in the grander view. So that's where I think some of the disconnect happens. And also the box is not super comprehensive, but that's how he teaches it. Yes.
Did the question about Roundup on our homework have like, was it one synonymous with this or was that totally different? Did that have,
I have to go back and look at it, but I think it was more similar to the Orlistat question that was on the previous homework. Yeah, so Roundup, that question was looking at like acyl reactions, acyl substitutions.
sorry.
It was like acyl substitutions. Yeah, what's up? So I think the quiz question is maybe the closest indication he's given to what he would ask about, where it's understanding that each round of biosynthesis takes 2 NADH, and from the number of carbons in the molecule, you can tell how many rounds it's gone through, and you can tell how many NADH. Which I overheard some people on the Wikipedia page for biosynthesis. But anyway.
What were the two things you said? Each one uses 2 NADH.
So when you know a fatty acid, it'll say like C10 or C12 or C32. That tells you how many rounds it's gone through, because every round is an additional 2 carbons, and each round requires 2 NADH. You add 2 on each round.
So where were the carbons added into this one?
So
If you're in the final step?
no, so the initial connection of them happens in that first step. And then the rest is simplifying 2 aldols down to 1 carboxylic acid and a carbon chain.
So the 2 added carbons are in the chain, we just don't see them?
I mean, you see them. So I could have kept going with the blue here. But see how this one is blue? It's this, which is this, which is this. Yes.
And so it takes 15 steps.
Yeah.
In your body, you're just like, you're just adding more carbons, or
To synthesize fatty acids, yes.
and like it's unlimited, so I could have, right now I can have like 3 trillion carbons.
So the limiting factor in how long it will be is the size of the active site. So it'll keep going until it hits a wall, and that's when it will fall off.
What's the wall?
There's a bug. The wall is like the end of the protein. So like proteins, he showed the structure of the protein in his lecture. It looks like this. That's the whole structure. This chemistry is happening on the inside of that, and eventually that chain will come out so far it hits a wall, and that's when it'll stop. Yeah. Yeah.
What's exactly going on? Because like in the next structure, it's not on.
So that's a reduction. We reduced our alkene to an alkane.
And it looks like there's the same number of carbons on like K to L as there are from H to I.
Yes.
So, but those are 2 different steps. So those are 2 different rounds. So there should have been another carbon added.
This is all 1 round.
Oh.
These are the steps that make up 1 round. Yeah. No. You don't even need to go into this much detail. His slides have less detail, and that is maybe a better place to start. Yeah.
So what
I think that if he is going to ask about fatty acid biosynthesis, it would be like the quiz question, where you use the number of carbons to determine how many rounds there are, and then you would answer a question about how many molecules of NADH were used in that.
So with that, would you provide the carbon just be 4 rounds?
Yes, 1 second.
that's a reduction.
Mhm. No, it's quiz 8. So quiz 8, the question was, which of the following are correct statements about fatty acid biosynthesis. And the correct answer, well, one of the correct answers is this third statement, which says that the synthesis of a C6 fatty acid requires 2 molecules of NADH. So it's not just divided by 2. And also, he made a correction. It's supposed to be 4 molecules of NADH. Basically, divide by 2. That's not right. C6 divided by 2. Yeah. So C6 means that 2 rounds happened because you have the initial round that creates C4, right? Because we have our initial connection create C4. Another round happened to create C6. So there were 2 rounds, each requiring 2 NADH. So it requires 4. So you can't just divide by 2 because you have to remember that the first step, you made a C4 instead of just a C2. Round. Yeah.
So whatever, like if it's C10, it
What comes initial? It'd be 6,
would be 6.
right? Hold on. C10 minus 4 from the initial round, and that took 2 NADH. You get C6. Then you had 2 rounds, or each of those is 2. So you have 3 rounds additional times 2 NADH equals 6 plus that. So yes.
So it'd be how, so for the NADH, it's just however many carbons there are minus 2.
Yeah. The synthesis of a fatty acid, a C6 fatty acid, requires 4 molecules of NADH. Yeah. Oh, finish your question.
So what we just, like what we ended with is C4.
Yes. Yeah.
So can you just like explain that?
Yeah. So the easiest way to do it is subtract 2 from the amount of carbons you have. So if you have a C10, it took 8 NADH. And that's because the first connection, you got 4 carbons from that, but it only required 2. And every round after that creates 2 more carbons on the chain and requires 2 NADH. So it's like a 1-to-1, except that first reaction. So you can do the number of carbons in the chain minus 2 equals the number of NADH. Yes. Other questions? Hallie.
Can we try out the same
Acyl substitution, yeah. Do you want to do like a practice problem from this homework or last homework? Okay. So this homework assignment, he gave you almost all the pieces that you needed to complete the mechanism. Major difference between that and last time, because last time he just gave you the substituents. And this time he gave you the active portions, almost all of them, and the substituents. So there were two correct answers that you could have here. You had, actually, so you had these two substituents, and then you had your SH and your phosphate. You could have connected these this way and this way, or this way and this way. I'm gonna work through the one he didn't do, because the one he did do is on mine. So for this example, we are going to attach our phosphate to this hexane. What is the key change I made here? Yeah.
Why did you not, connect with? Why didn't they go together instead of like-
Because they're both the reactive parts. And if they're on the same molecule, you would have an intramolecular reaction. Too big for our britches. So what is the key change that I made here in drawing on my phosphate group? I had to put a linker in. What linker did I add? Double bonded oxygen. We need this double bonded oxygen because that's the carbonyl where our reaction is going to occur. We gotta have one of them bad boys to do acyl substitution. So, requirements for acyl substitution. You need an ester of some kind, thioester, amide, ester, one of them's. And then you need a nucleophile. So, first things first, our nucleophile is gonna get deprotonated. So we'll have some base come in and deprotonate. Now that we have a nucleophile, and what's our key thing about carbonyls? The carbon of a carbonyl acts as an electrophile. Should sound a little familiar maybe by now. Yes, no, maybe so. Julia? Yeah. Well, when we were making our reactants, we were putting together the stuff that he gave us. We know that in order to do an acyl substitution, we need to have that carbonyl. Yes. So, nucleophile, check. Electrophile, check. They're gonna talk to each other. we have our tetrahedral intermediate. This is going to collapse and kick off our leaving group. Ta-da. Questions? Comments, concerns? Up, middle, down? So the squiggly lines are what Dr. Begley and chemists everywhere use to say something connects here. And so for our purposes, that's where he's saying you would connect the rest of this molecule. Yeah. The ester will always go with the phosphate group. Because the SH is our nucleophile, we're going to turn the phosphate into our ester.
Does it matter that the right specific?
So like with this, how I get from this here to here, all I did was what else would we like to cover? What? Yes. Yeah.
From this side.
No. As long as you have the right connectivity, it's okay if you don't yet understand the like spatial stuff. Don't worry about that. Yeah.
This will be uploaded and recorded later.
Hopefully.
Oh,
I'm bad at technology. The PDF of like all of this work, definitely, that I know how to do. The video,
we'll take it.
I'll figure it out. Hallie. How what? Yes. So this whole group, OPP for short, OPP, biology's greatest leaving group. So other leaving groups that are helpful to know, your halogens. So that's like bromine, fluorine, iodine. They love to leave. Another one is hydroxy, because that leaves and becomes water. And then OPP is biology's biggest leaving group. CoA is another good one to know, though. No. So if we wanted to label functional groups with this, we could say we have a thiol. In this case, if it was an OH, it would be an alcohol. This whole group is a functional group. So you can't separate them up. Yeah. This one here is a thioester. Those are all the ones on this molecule you would need to know. I could just start listing them, but I don't know if that would be super helpful. Yes, but not as a functional group. Yes, they're alkenes in that it's a double bonded carbon, but this whole group, I believe, is called naphthalene. Yeah. No. So you definitely would not need to know that. No. This one doesn't have a lot of functional groups for you to label. It's not a benzene. So benzene is a 6-membered ring with alternating alkenes. This is a hexagon, but not a benzene. And it also has this connector bit, which actually means that it's a set of fused rings like the naphthalene.
No, not that one. The one in the map. Would you want us to label that?
No. He would give you an isolated benzene because in his head, he sees that as naphthalene. And he doesn't expect you to know naphthalene. Other questions? Man, I really thought I was going to be here till 10:30, but if you guys don't have questions, I schedule you guys to have my life until 10:30. So now is really your chance to be answering those questions.
Problem set, problem set 6, question 6.
Problem set 6, question 6. Question 9. Terpenes.
I don't understand how to say this.
So with terpenes, you're going to try and get the folding to be as close to the final product as you can. So for this one, we have So hold it. I would say the best first step with this is counting your carbons. That way, you know what you're looking for. This is how I would number it. You don't have to number it if this doesn't make sense to you. Number it like this if it doesn't make sense to you. I know that there are 8 carbons in the chain and 2 methyls coming off. So when I look at our final product, our final product has a 6-membered ring, one methyl at the top, and 3 at the bottom. 3 carbons at the bottom. So I'm going to try and make a structure that looks somewhat similar to that. So we can go back through and number and make sure that we haven't lost any. And we want to make sure that our connectivity is still all the same. So in our first one, we had this double bond between 6 and 7, and we had an offshoot of 6. Once we folded, we have a double bond between 6 and 7 and an offshoot of 6. We also have 2 and 3, offshoot of 2. 2 and 3, offshoot of 2. Now that we're folded, it's kind of like we've primed ourselves for reaction. So OPP is a good what? Leaving group. So guess what it's going to do? Leave. Goodbye. Let me do it in red. So I'm just going to take all of this and duplicate it. If that left, what have we formed? If it took the electrons from here, what happened at poor carbonate? It's a cation now. It is now electron deficient. And alkenes are what? Rich or deficient? Rich. So our electron rich, aka nucleophile, is going to attack our electron 4 electron. So that's going to go there. And we are going to make our 6-membered ring. Now, if we took the electron, yeah. This here, electron poor electrophile. So it's E minus poor E plus, big E plus. So what am I missing in this structure that I've just drawn? It has to do with the alkene that we just moved. Because we just took electrons away from this carbon and this carbon. And we only put a new bond on the pink carbon. Yes. So now we have a cation here. What of our favorite friends is always in solution? Water. Which becomes H plus and OH minus. OH minus is a nucleophile. So it is going to attack here. We are then going to reduce our alkene. So reduction, what do we use as our reducing agent? NADH. And it is going to give us, well, it's not really a reduction. Maybe I shouldn't call it that. It's really more of a quaternization. We'll call it protonation. So what does our oxygen have? 2 of. Lone pairs. Our lone pairs can act as a nucleophile. Our carbocation is an electrophile. They're going to attack and neutralize that carbocation. The pKa of a proton on a positively charged oxygen, really low. It's getting out of there. So we'll just say it leaves. And we have our final product. Because acyl substitutions use carbonyl groups. And yes. That's my friend Erin. Other questions? We did an acyl substitution. This is an acyl substitution. You doing okay? Nothing in this class. The Hozier concert's before your final. It's the night before your final. You're welcome, Howie. Like, do this every week? No, I was not planning on doing that. I do, surprisingly enough, have other obligations. Well, because I knew if I waited till the final, that would be a lot of content to cover. So I was hoping that by doing this one like halfway through, the final will be less scary. Yeah. Yes.
Can we do where the first question?
I was also not pleased with this question. That's okay. So whether he okay, I don't know. I'll figure that out. It'll be somewhere attached, and I'll probably make an announcement when it's been posted. So with this one, question 10. It was supposed to get you to start thinking about which reactions need what reagents. So nucleophilic substitution doesn't need any reagents. Acid-base chemistry doesn't need any reagents. So the things that are in the reaction that aren't the thing we care about. So like, you know, all the X minuses and the eight, like those are like reagents. So when we say there's a base involved or an acid involved, it's there, but it's not the thing we really care about. So when it's just the picture, that's because there's no reagents. So like the last two, he says explicitly that there's a base involved and O2 involved. So O2 is an oxidizing agent in the same way that NADH is a reducing agent. So with the first one, what you were meant to see is you have a carboxylic acid, acids are proton donators. And you have NH2, which has this space or capacity to accept a proton, which means it can act as a base. So because there's no reagents, nor are there any other structures drawn, you know that the reaction has to happen entirely within this molecule. So we are going to, oh God, deprotonate our carboxylic acid. So this becomes O minus, and we're going to protonate our amine. So that becomes NH3 plus. Do you feel good with that one? Can I do the next one? Yeah. Yes. I will put it up either today or tomorrow. And then I'm also going to do some pages on concept reviews. So like aromaticity, chirality, resonance, functional groups, NMR. Which honestly, I could probably do just a whole session like this about NMR, because NMR is a lot easier to explain in person. Like you have to think of it kind of like a puzzle where you work through the steps and eventually you get your answer. This is the next question. Sorry.
So we just leave it as that, we don't have to like hold it and connect them?
Nope. We're gonna connect next one. Because, like I said, Br, halide, good leaving group. So that's gonna attack here and kick off our leaving group. And make this. And Br minus floating around. Which is nucleophilic substitution. Because we have our nucleophile and we are substituting what is attached to this carbon.
What happens first?
Yes. So it attacks and kicks out Br. Yes. So then our next one also doesn't have any reagents. So it's going to happen entirely within this world or this molecule. We have an electrophile and an aromatic system. Would you like to wager a guess about what happens? Electrophilic aromatic substitution, exactly right. So we are going to use our alkene to attack the electrophile. It's going to make this intermediate. That's not right. Which is going to lose our proton to restore aromaticity. And there we have our final product. So the next one tells us that it needs a base. What we're going to do is use that base to eliminate Br. Base is going to remove one of our hydrogens, putting that electron back in and kicking off Br. There's another way we could draw this mechanism. Well, no, there's not, because we know it's base catalyzed. But for general elimination reactions, there's 3 different mechanisms. And they are all featured in the study guide. Finally, the last one uses O2, which is an oxidizing agent. Which gives you a hint that this reaction will be oxidation. We know that oxidation is losing electrons. So if we were to draw the intermediate where we've lost both protons, we would then also lose 2 electrons. We have a negative and a plus in the same boat. So they are going to cyclize. And you get, I'm just going to draw it as a circle, but know that it's not. No, don't do this. It's because I don't trust myself to draw a 1, 2, 3, 4, 5, 6, 7 octagon. I guess I could try. Something like that. We could get into the exact mechanism if you really want to know, but we haven't covered an O2 oxidation in the class, so I don't think you need to know it.
Minus 2H plus is that
No. So these dotted lines mean that it's bookkeeping. It's not an actual mechanistic step. But this would be a mechanistic step. If we look at the study guide, I have that separated out for you guys. So like, there's the oxidation where it's there used to be a laser pointer option. Oh, there is. Okay, so the oxidation bookkeeping is these like dotted lines. And then usually the last step looks a little mechanistic. The mechanism, the example that I chose to draw out uses NAD plus, not O2. But the mechanism, we can see there's base deprotonation. These electrons move, and then you have this whole hydride group. So you're not just getting rid of a proton, you're getting rid of a proton and its electrons. So in the same way that NADH is a hydride donator, NAD plus is a hydride acceptor. So that whole hydride unit can go back onto NAD plus, and we basically see the reverse of the steps we took in an NADH reduction. And in this, we restore NADH from NAD plus. Mm-hmm. You're welcome.
Just like an 80 plus. they can have that still go to.
Yeah.
And that's why. I don't understand how the S's end up with.
So one of these will just get deprotonated. So we have our carbon chain. You're welcome. So one of them will just get deprotonated. And from that, we get S minus. But we have an oxidation. So O2 looks like this. O2 let me draw it out. Let me double check my mental math here. Yeah, so the mechanism of this is a little more complicated because it uses radicals, which is maybe not a subject that you've encountered before. Radicals are when the bond breaks up into its separate electrons. So another way that O2 can be written is when we use these half arrows. And these half arrows indicate the movement of just one electron. So then we get a radical and a radical. And basically what happens there is it's going to abstract the proton. So this is going to take one radical from one electron from here, one electron from there, and the other electron will go here. I'm telling you, this is more complicated than you need to know, but I'll walk you through it because you're curious. So now we have HO O dot. Oh my God, my phone's blowing up right now. I don't really know if I want to go further with this example. Okay. Okay. We'll stop there. It does happen. And you don't need to know the exact mechanism because it's much more complicated than we need. other questions? Okay, I'm gonna stop the recording, but if you have other questions that come up, let me know.